Start, please. Now just now we did the lab method, now is the industrial manufacture of ammonia. It is called the Haber's process. Industrial manufacture of ammonia is called Haber's process. In this, it is a synthesis reaction, that is the elements are directly combining and forming the compound. It's a reversible reaction, as you can see, and exothermic reaction. So the nitrogen and hydrogen, it is taken in the ratio of 1:3. 1 part nitrogen and 3 parts hydrogen, 1:3 proportion. Sources of nitrogen by distillation of liquid air, and fractional distillation of liquid air, nitrogen is taken out, and hydrogen from water gas by Bosch's method. So these two are taken and then they are compressed to a, this is a pump, it is compressed to, compressor is compressed to a pressure of 200 to 900, depends on the size of the plant, whatever, it's more than 200. Usually the optimum pressure is 250, okay, 250 atm. Now this compressed nitrogen and hydrogen in the ratio of 1:3 is passed through this chamber. This is the catalytic chamber. In this reaction, what is used as a catalyst? Iron, finely divided iron is used as a catalyst. So reactants are N2 and H2. This is the ratio 1:3. And what is the product? Product is ammonia, NH3, right? And the reaction I have just written over here, this is the reaction. Reaction is exothermic, 22,400 calories of heat is produced. It is a reversible reaction. And you can see one more thing, that the volume of the reactant is 1:3, 1 mole, 3 mole, and this is only 2. So the volume is half, becoming half. Here the volume is twice, 4 moles reduced to 2. That means the volume decreases in the product, the reactant and the product. Now the temperature, because it is an exothermic reaction, ideal temperature would be low. It should be low temperature. Low temperature, if the reaction is exothermic in nature, it will favor means a low temperature will favor the reaction. But what happens is, nitrogen and hydrogen, the two reactants, they have to colloid first and then only the reaction will take place. At a very low temperature, what will happen, or under normal temperature also, the collision is not enough. That means the kinetic energy of the molecule is less, so it has to be heated a little. If it is heated, then the molecules will acquire kinetic energy and the collisions will be more effective now. So what is the optimum temperature that is used? It is found that the best result is obtained if it is heated to 450 to 500 degrees Celsius. So that is the optimum temperature, 450 to 500. And what is the optimum pressure? Why do we need the pressure? The pressure is needed because, see, the volume is reducing to half. So in order to make the reaction flow in a forward direction, pressure has to be applied over here. That will favor, if a pressure is applied on the reactants, that will favor the reaction in a forward, that will push the forward in a forward direction, because the volume of the reactant products are half the volume of the reactants. There is a fall in pressure over here. So initially we have to keep a high pressure, that is 200 to 900, ideally 250 atm of pressure is used over here. So this is 200 to 900, means above 200, 900 atm pressure. Catalyst is used as iron filings. In many books you will see other things like Fe2O3 etc. written. I would prefer you write Fe filings, finely divided iron, finely divided iron, finely divided small pieces, divided Fe. This is the catalyst, and this just increases the rate of reaction. It has no effect on the product, of course. Amount of ammonia produced has no, this has no impact on that. Only the rate at which the reaction is taking place, that is increased. Then to help the catalyst, there is a promoter. This molybdenum is used as promoter. A small amount of molybdenum is mixed with the iron filings. That helps, increases the efficiency of the catalyst, that is iron. Then what are the precautions that you have to use? These two. The precaution is the gases should be free of carbon monoxide, carbon dioxide and H2S. These three are the impurities which poisons the catalyst. So, nitrogen and hydrogen should be in a pure state, should be free of CO, CO2 and H2S, and then they are compressed in over here. Here is the heat exchange. Here this chamber is called the heat exchanger or catalytic chamber. This one is the catalytic chamber. Okay, in this what happens, the gases which is entering in 1:3 compressed gas that goes inside this, and here is FeO. This is packed with Fe and MO, and externally it is heated to, initially it has to be heated to reach that temperature 450 to 500. Now after that it can be switched off because this reaction itself becomes exothermic and starts generating heat. So the gas converts into nitrogen and hydrogen. Nitrogen and hydrogen converts into ammonia, and the heated gas has to be cooled down now. But how much? Only 15 to 18, 16% converts. Nitrogen and hydrogen converts into ammonia. Rest of the gas remains as unreacted nitrogen and hydrogen. So the gases which are coming out from here, it is a composition of three, mixture of three. That is NH3, ammonia, which has combined, N2H2 has combined ammonia, nitrogen, unreacted, hydrogen, unreacted. Now this is passed through to a cooling, a condenser with cooling pipes over here, right? And the ammonia has a very low liquefaction point, means it, whereas nitrogen and hydrogen turns to liquid at a very, very low temperature, means nitrogen at minus 196 degrees Celsius and hydrogen at minus 253 degrees Celsius. So an ammonia only at minus 33 degrees Celsius only it becomes liquid. So a temperature at that, the ammonia liquefies first and drops down over here as liquid ammonia, whereas the two other gases N2 and H2 remains in the gaseous state. This is again recycled like this through the pump, compressed through the pump, because you have to apply that pressure 250 250 pressure, and then it goes back into the catalytic chamber. Again the same process is carried on. So the reaction N2 plus 3H2 is 2NH3 with this exothermic reaction 22,400, means 22,400 calories. Initially has to be heated to 450 to 500 degrees to start off the reaction. Then it becomes exothermic in nature. What are the gases that has to be removed? CO, CO2 and H2S, hydrogen sulfide, because they poison the catalyst. The catalyst is Fe, promoter is MO, and then the gas is passed and liquid. Another way the ammonia can be separated from nitrogen and hydrogen is directly if it is dissolved in water. If the three gases are put inside water, then pass through water, then what happens? Ammonia is highly soluble in water, so ammonia dissolves in water forming ammonium hydroxide, and nitrogen and hydrogen do not, they are insoluble in water, so they come out as it is, as gases. And then from ammonium hydroxide, ammonia can be retrieved back. So that was Haber's process, the industrial manufacture of ammonia. হয়ে গেছে, good.